Wow, it's light in here today.
Yeah, what happened? Whoa. That first test was kind of rough, I guess.
Man, I did the homework.
You're not getting rid of that easily.
Yeah? Well, look, I'm going to give the test back, but I'm not going to give them back yet. All right? Let's just get through today's material, and that way we can, have a little time at the end to talk. If I start talking about the exam, I'm just going to go off, and then next thing you know, it's going to be like I'm going to have 30 minutes left. So let's get through today's material, and let me make sure I am recording, my mic's on. I feel like I'm forgetting something. All right. So today is a good day in terms of where we're headed, where we're going. Today's a good day, because everything up to this point, if we wanted to take a derivative, we had to apply the limit definition. The limit definition being limit as h went to 0 of f of x plus h minus f of x all over h. That was 2.2, right? Yeah. And we saw that could present some issues with the algebra. And depending on the complexity of the function, the algebra could get pretty challenging. Well, there turns out that there are shortcuts, all right, to doing this. So you don't have to actually use the limit. Each one of these shortcut formulas, and there are, 11 of them here in this first section, these shortcut formulas can all be proved using the limit definition. And I am going to prove 2 of them to you today. I'll do it after we go through each one of them and look at examples. But just to show you that these formulas don't just fall out of the sky. They're not just there. We didn't find them on a cave wall. Someone wrote them down for us, and we actually had to come up with these formulas. But let's just go through them first, see how quick and easy it's going to make our life, and go from there. These are known as the basic differentiation formulas. So the first one says that the derivative of a constant is 0. So I'll say first formula here, it's written like this: the derivative of any constant is 0. Now let's just think about this geometrically. Geometrically, let's think about this. What we're saying is that if you take a function, f of x, and you define it to be a constant. So give me an example of a constant function. F of x is 5. Okay, good. And that's exactly what I was thinking. As a specific example, f of x equals 5. If I were to ask us to graph that, you would go up 5 units on the y-axis. You would draw a horizontal line like this. And that would be the function f, wouldn't it? It'd just be this flat line like this. And now you say, what's the derivative of that? Well, the derivative, you go to any point on the graph and you talk about the slope of the tangent line. The slope of the tangent line should run parallel to the line itself, and the slope of the line was 0. So anywhere you go on this curve, or on this straight line, the derivative should be 0. Make sense? So anytime we have a constant function, we take its derivative, the answer is 0. So let me give you some specific examples over here. What is the derivative of this function, e to the pi? So I need to tell you to take the derivative. Do you remember the notation with the prime mark? The prime meant take the derivative. Okay, so take e to the pi and take its derivative. What is it? What's e? What's e from college algebra? E is a number, right? That's just a number. It's like 2.718 something. And if I take the number 2.718 something and raise it to the pi, which again is another number, I should get a number, shouldn't I? This doesn't look like a constant, but it is, right? So the derivative of that should be 0. What's the derivative of negative 10? 0. Anytime you have a constant by itself, the derivative is 0. And that's it. That's the first rule. Easy does it. Now the second rule is, what is the derivative of x? And if you look in the notes, it says 1, right? It says 1. Let's try and verify this using the geometric concept here. If I were to graph this as a function, f of x equals x, that's one of the important functions from college algebra called the identity function. And that's what it looks like. And the slope of that line is 1, isn't it? And because the slope of that line is 1, if you go to any point on this curve, anywhere, and talk about the slope of the tangent line, it's going to be parallel to the line itself, so it should also be 1. So the derivative is 1. So you might see me write it like this. The derivative of x is 1. Is that all right?
But it'll only work if it's x by itself.
That's just x by itself, not 5x, not x squared. That's just x. Okay? Well, we'll see that quite a bit. Yep, we'll see that quite a bit. Let me just make sure I get to the next one. Okay. All right, the next one, and this is probably the most important rule for today. All right, so I'm going to put a star next to it, third one. This is known as the power rule. Yeah, this one right here is used a lot, and you'll hear me say it in my homework solution videos, like, oh, you just do the power rule, and this is what I'm referring to. And it's also important to note that this is the power rule for differentiation, because there is also a different power rule in Cal 2, which we call the power rule for integration, which is the reverse process of differentiation, which is what Cal 2 is about. So when you talk power rule in Cal 1, we do this rule. Power rule in Cal 2 is a different rule. They're connected, don't worry. I mean, they do have similarities. And so here's what it says. If you're trying to take the derivative with respect to x, and this was Leibniz notation. This is the way he said it. If I'm trying to take the derivative where x is my variable of x to any power, okay, so n can be any number, then the answer is nx to the n minus 1. That's it. Now I'm going to show you a couple of examples of this. After we do a couple of examples, after I get through all the rules, I'm going to come back and I'm going to prove this rule. I'm going to show you where it comes from, okay? But let's just use it first. So here's an example. Let's say that we have, what is the derivative of x to the 5th power? Well, according to this rule, that looks like x to a power, right? X to the n. So this should just be 5 comes out, and then subtract 1 from 5. So to the 4th, 5x to the 4th. That's it. We're done. Easy does it.
This is the power rule, right?
This is the power rule.
You showed us that before, right?
I did. I gave you kind of a hint, like a sneak peek, that we were going to see this, right?
Yeah.
Let's do some other variations of it that maybe aren't so natural. Okay, how about this? Square root of x. What's the derivative of the square root of x?
Well, that's the same as x to 1/2.
Yeah, first let's realize that square root of x is actually x to the 1/2 power. So watch, I'm going to rewrite this, but I'm not taking the derivative. I'm just rewriting the square root as 1/2 power. Right?
Oh, that's nasty.
And now we can use the rule. As long as we have x to the n, we can use the rule. So n is 1/2 here. We're going to bring the 1/2 out front, and then we're going to subtract 1 from 1/2, right? So it'll look like this. 1/2 comes out front, x to the 1/2, take away 1. What's 1/2 minus 1? Negative 1/2, right? So this becomes 1/2 x to the negative 1/2, which is a correct answer. This is right. You could be done at this point. But because of where we're headed with this, we're going to need to be able to manipulate this sometimes into other forms. So let's also be comfortable with the idea that this is the same as 1 over 2 x to the positive 1/2. So that's just dropping this negative exponent down. Remember, negative exponents drop down? So when I drop it down, it joins the 2 that's already down there, and the only thing on the top is the 1, right? So I could write it this way. And I could even go a little further and switch back to the the radical notation instead of this notation. What is this notation? Anyone know what this is called when you have like this versus this? This is radical notation. So you have radicals in there. This is rational exponents. So your notation, you're using rational exponents. Your exponents are rational numbers, fractions. Okay, those are the different notations there. Okay? Any questions on how I got from here to here? Let me point something out. This problem comes up a lot. You have to take the derivative of the square root of x a lot. In Cal 1, in Cal 2, in Cal 3. It happens that function just always appears. So I would like for you to just memorize this. Don't worry about all this stuff in here. I mean, be able to do it, okay? But just in your mind, anytime you take the square root of x, it is just 1 over 2 root x. 1 over 2 root x. The derivative of root x is 1 over 2 root x. Root x? 1 over 2 root x. Just kind of get that programmed in, okay? Save yourself some time. All right, the next problem I'm going to put up as an example was a test problem. What is the derivative of 1 over root x? Now you had to do this on the test by setting up a limit. And I don't recall right off the bat how many of you got this right or not. I know in my other class this was one of the most missed problems, but this was also a homework problem. The only difference was that in the homework it was 1 over square root of t instead of 1 over the square root of x. Either way, we're not going to use the limit here. We're going to use the shortcut. All right? Yes? So the big mistake people will make with this is they'll say, hey, look, I've got 1 divided by square root of x. 1 is a constant. The derivative of 1 is, it's a constant, right? What's the derivative of a constant? 0. We already said that. 0 over, and then what's the derivative of this? 1 over 2 root x. But 0 over anything should be 0, right? Completely wrong. Okay? The reason why is because you were just trying to take the derivative of a quotient. That's division, right? You cannot assume, do not assume that if you're going to take the derivative of a quotient that you can just do the derivative of the top and bottom separately. That is a huge mistake. In fact, we have an entire rule for dealing with that, and we will do that on Wednesday. So anytime we have a quotient, you cannot just do top and bottom separately. However, we can rewrite the problem as x to a power if I just bring that up. So how could I rewrite this here? X to the negative 1/2. Negative 1/2. Look, it's the reverse of this, right? We went from here to there. Same thing. I'm just going to go back up, and I'm going to push it back up as a power. So 1 over the root of x is the same as x to the negative 1/2, and now let's take the derivative. So what's n for us here? Negative 1/2. So I'm taking the derivative, no more derivative mark here. Negative 1/2 comes out, x to the negative 1/2, and I'm going to subtract 1. And what's negative 1/2 minus 1? Negative 3/2, right? So you have negative 1/2 x, negative 1/2 x to the negative 3/2. And that would be the answer. I mean, that's okay. I can actually do a little more, though, if I want to try and make it look pretty. I could go, yeah, let me drop it first. I can make it like 3/2 like that. See? 3/2, is that okay? That's just dropping it down. And then I could go back and remember what this means. Doesn't that mean square root of x cubed? That's what that means. Remember, the 2 out here, we don't usually write it, but the denominator of a rational exponent is the root, and the numerator is the power. So, there.
Would it be the square root?
It's the square root.
Where'd you put the 2? I'm in front of that.
Oh, no, I haven't done it. I was just telling you what this is. This right here is this. Let me continue here. This is negative 1 over 2 square roots of x cubed. And I can even go a little bit further. The square root of x cubed can be simplified. Because this right here is really x squared times x, right? That's x cubed. So you have square root of x squared. That can come out as an x, and you still have 1x underneath the root. And that's the answer you should have got on the test. Yeah. Should have looked like that. Yes? Okay. Any questions on going from here to here, though? Let me go back up here. This right here, do you agree with that? Do you agree with that? Okay, now this is square root of x squared times square root of x. I can split it into two roots. Square root of x squared is just x, and then root x. Yeah? That all right?
But it would have been okay to leave it the original way for this purpose.
Yes, but you need to be able to get from here to here without any issues. Yeah, you need to be comfortable with this. It's not a matter of this is okay and you can survive with that. You need to be able to get here, but this is not a calculus topic. This is a college algebra topic. This is just rewriting something, right? That's all it is, using different expressions.
So is that in its most simplified form, I guess? Is that what you're saying?
This is in radical notation. This has no negative exponents, right? See, here we had negative exponents. Some people don't like negative exponents, so we do this. And then some people want to be able to get to radical notation, which is this, but hey, that's not completely simplified in terms of radical notation. This is more simplified. So, all right. And we could keep going, right? Let me do one more. Let's do the derivative of 1 over the 4th root of x to the 3rd. It's the derivative of that. So you're going to rewrite it first, right? What are you going to rewrite that as? Did you say 1 over? Yes, you can do that first? Okay, just write it as 1 over x to the 3 over 4. And then you could rewrite that as just x to the negative 3/4, right? And I haven't taken any derivatives yet. I'm just rewriting everything.
Sorry.
It's all right, but let me make sure everything's still there. Okay, we should be all right. And now we can apply the rule. So negative 3/4 comes out. X to the negative 3/4 minus 1. You're going to be having to do this quite a bit. Subtracting 1 from a fraction. That happens a lot in Cal 1. Subtract 1 from a fraction. When you do that, does everyone realize that this 1 will always turn into whatever this denominator is, right? 4, just that number over itself. 4 over 4.
That'd be negative 7 over 4?
And that will be negative 7 over 4. Yes. So just get used to subtracting 1 from fractions. It's going to take place a lot. So this is going to be negative 3/4 x raised to the negative 7/4, which is the same as negative 3 over 4x to the positive 7/4, which I can write as the 4th root of x to the 7th. Right? I'm going to come up here with that. This is negative 3 over 4 times the 4th root of x to the 7th. And I can do the same thing I just did a second ago. I can split up x to the 7th as what? This is scratch work over here. x to the third times x to the, whoa, hold on. Let me do it this way. I'll do x to the fourth times x cubed. Is that okay? And then I'll split that into 2. And so I'll have the 4th root of x to the 4th will be just a single x, right? And then I'll be left with the 4th root of x cubed. So this right here becomes negative 3 over 4, what? X times the 4th root of x cubed. This is correct, this is correct, this is correct, this is correct. Any questions? You're just going to have to get used to doing enough of these where you get comfortable with it. And
So that would be our final answer, right?
yes, that's it. Yep. A lot of times on the test, I'm looking first for what I call the raw derivative. Who's asking me this? Which is just like, did you get the derivative correct, number one? And then your simplification would be kind of the secondary thing I look at. And it depends on the context of the problem. If I'm just saying find the derivative, then that first part answer would be correct. But a lot of times, we're not going to be doing just the derivative. We're going to be doing something with that derivative. So you're going to have to be able to simplify it a little bit. So, all right, you ready for the next rule? That's the big one. That's the big rule today. The next one is called the constant multiple rule. So let me explain what this one is saying. I'm going to just write it up here, like an example. The constant multiple rule says this. What if we have, instead of just like x to the 4th, right? Instead of just x to the 4th, we want to take the derivative of 5 times x to the 4th. How does that constant affect the derivative? What's that? Will it just multiply the answer times 5? Well, if we do this, if you take the x to the 4th out of there, right? What's the derivative of 5? 0, right? The derivative of a constant by itself is 0, but when you attach a constant to a function, it's no longer 0. It's just going to come along for the ride. So here's what's going to happen. The 5 can actually be ignored, but it has to come with us, okay? And we're just going to focus on taking the derivative of the function, which is x to the 4th. What is the derivative of x to the 4th? 4x to the 3rd, but the 5 is going to be sitting there just waiting to multiply times that. And 5 times 4 is 20. So you get 20x cubed. Got it? So constants by themselves, the derivative is 0. Constants attached to functions, they just come along with you, and at the end they multiply through. That makes sense? Yes?
From the 4x to the power of 3, you got that from like subtracting a...
This was the power rule that we just covered. 4 comes out front, take 1 away from this power.
All right, just
That's
sure.
this, yes.
Yeah, just being sure.
Yep, that's what it is. Now look, in all honesty, we don't want to go through and write these two things down, okay? We just want to go straight from here to here. Because if the 5 is going to come along with us, when the 4 comes out, it hits that and becomes a 20, right? Hits it, I mean multiplies, right? Multiply the 4 times the 5, that becomes a 20, and then just reduce the power on the exponent by 1, and you're done. Okay? And this will occur for any function. Doesn't matter what this function is, as long as this is a function, it's not just all one big constant, this will apply. Let's do another one. How about take the derivative of negative 4 root x. Yeah, so if you follow what I just told you a second ago, you're just going to bring the negative 4 with you, right? Times. Now the derivative of the root x, which I told you just remember is 1 over 2 root x. And now the question is, can you simplify that a little bit more? Yeah, you're going to have this 2 goes into here right, twice, because that's really like a 4 over 1. So you get negative 2 over root x. That's what that would be. How about this one? 9 over the cube root of x. What's the derivative of that? So somebody tell me first how I can rewrite this before I take the derivative.
9 over
X to the 1/3.
1/3.
And then bring it up to get your negative 1/3. Like bring it up from the bottom.
So, that would be
9x to the negative 1/3. Still haven't taken any derivative yet. Any questions? Go ahead and do your power rule now, right? And the 9's going to come along. So this negative 1/3 comes out. What happens when I take negative 1/3 and multiply it times 9? Negative 3, right? Don't I get negative 3? So I'm just going to get negative 3 out front. X to the, I have to do negative 1/3 and take away 1, which is the same as 3/3, right? Which will be negative 4/3. Yeah, we're not adding it, we're subtracting it. Yeah. So this becomes negative 3x to the negative 4/3. And of course, I could go on and simplify that, but I'm just going to box this up. We good? And we can just keep going all day long, all right, with this stuff. But this is it. This is the principle of it. If you have a number attached to the front, you just bring it with you. If the number's by itself, there's no function, the derivative is 0. All right, next rule. The next rule tells you how to deal with when you have more than one term. So let me show you on this rule. It said, look, if we were taking the derivative and we had a constant attached to the function, there was multiplication there, that you can just pull the constant out and then take the derivative of the function and then just multiply that constant through. That's the way it's written, like mathematically. This next rule says, hey, if you're taking the derivative and you have a function added or subtracted to another function, if there's addition or subtraction between them, you are allowed to just do the derivative of each one separately and add or subtract them together. That is a very good thing, because it does not work that way for multiplication. All right? But if it's addition or subtraction, we do them individually, and we're done. So let's take a look at that in action. So what if I have 3x, let me look at this is the bonus problem here. X cubed plus 3x squared. X cubed plus 3x squared. Take the derivative of that. I don't remember if anyone got the bonus right. I'll have to look. I graded those on Wednesday night, so I mean, it's been quite a while since I've looked at those. If you did it the way I expected you to do it, you did the limit. The limit is h goes to 0, and you work through the whole thing, and then you got an answer and set that answer to 0. And so I know some people got it. I know also some of you took the shortcut, which is you use the rule that I'm introducing you to today, which I may have given you something for it, but it's kind of cheating. I wanted you to use the limit. Yes.
I don't know, did you specify that you wanted?
I didn't specify, but I think it's implied because, you know, if we haven't covered it in the class, you know, like on the next test, if I say take the derivative and I expect the limit, I need to say that on the next test.
Yeah.
And I will. I will say use the definition, or I'll say, you know, I'll either say use the definition or I won't say it. So if I don't say it, you want to use a shortcut. All right, so let's do this one the easy way now with the shortcut we just got. It's the sum or difference of two functions, right? It's x cubed plus or minus. It's a different function, right? So the rule says I'm allowed to take the derivative of each one separately and just add the two answers together, right? So derivative of x cubed is 3x squared. And plus the derivative of the other one. So the 2 comes down, you got a constant in front, it's going to hit it, so 6, and then x. That's it, you're done.
That's it.
Why
That's-
didn't we
we're
avoid
done.
this, like, a long time ago?
That's a good question. Remember I said part of Cal 1 you have to be tortured through the limit. It's part of the initiation.
You sound like you're talking about a cult, not a class.
Yeah, you're right. It is kind of. Look, remember I'm the messenger, okay? I'm the messenger. And the limit is important, all right? Because the limit never goes away no matter what calculus class you take. The limit is always there. And so it's a foundation for all of what we do in a lot of mathematics, not just calculus. So if you're never shown the limit and you never have to actually like think through it, then later on you're not going to be able to think through harder things. All right. So this can go on and on. I can just keep adding things together, and right? And how about we try something a little more challenging? How about we do something like this? How about 5x squared minus the square root of x plus 7 minus x all over, you thought I was done, over the cube root of x. I would like to know what the derivative of that is. Just to appreciate this, okay? Just for some appreciation of how good this rule is now, I just want to write something down for you. Limit h goes to 0, 5x plus h squared minus square root of x plus h plus 7 minus x plus h. Do you know what I'm doing here? Over cube root of x plus h minus 5x squared minus root x plus 7 minus x all over cube root of x, all of this over h. Would you want to try and figure out what that is? Can you imagine what this would be like? Common denominator, right? You get a common denominator first. Imagine just multiplying this by that denominator up here and down here, and then trying to put it together. That's algebra that I don't even want to mess with. That I don't even want to mess with, all right? So could it be done? Maybe. I can't promise you that it could even be done, that we would be able to get it, all right? It may not, it may be impossible for us to get it. But the rule is important because the rule allows us to do this without doing it. But that means the rule had to be proven, and the proof of the rule is really important. But luckily for you, we're not doing the proofs. You should be happy we're not doing the proofs. That would be a different, that would be a totally different ballgame. You don't need to know the proofs, you just need to know the rules. Okay, so the rule says that I just need to, right now, here's what I can handle. I can handle taking derivative of a constant by itself. I can take the derivative of x to the first power, right? X by itself, I can take the derivative of that. I can take the derivative of x to any power. I can do a constant times x to any power. And I can do a bunch of different things added or subtracted. I cannot do division yet. I've been told I can't do that. However, algebraically, if you have a single term in the denominator and multiple terms in the numerator, you can split this into multiple fractions, can't you? You cannot do it the other way around, right? If this were on the top and all 4 of these terms were on the bottom, you cannot split that into 4 different fractions. Then we would be stuck. We would not be able to do the problem until next class. But we can do it today, this one, because I can write it as 5x squared over cube root of x. You know what? I'm not going to write cube root of x. I'm going to write x to the 1/3. Is that okay with you? Minus x to the 1/2 over x to the 1/3 plus 7 over x to the 1/3 and minus x over x to the 1/3 derivative, right? That's what I want. I talked about this in my other class. I don't think I've mentioned it to you. I have this this real big problem. I don't know, my brain just keeps doing this, and it's always done this my whole life. I hate it. When I write fractions, I switch back and forth between these two notations. And it's totally subconscious. I don't even think about it. And I wish I was consistent with one. So if you see me using two notations here, I know. There's nothing I can do about it. All right? You probably didn't even notice it, did you? Okay. They're both correct, though. You can use either one. All right, so I did that. Do you see that? Do you see why I did that? Right? Yes? See why I did that? Yes? No? I'm going to use this from college algebra, right? I can always take x to a power over x to a power, and I can use this rule. I can subtract the powers, and then I'll get x to a power, right? Just one x to a power. So what about this one? X to the second over x to the 1/3. You take 2, you subtract 1/3. You have to get a common denominator. 5/3. 5/3. 2 minus 1/3 is 5/3. Now look, you might have to do this, all right? I know that when I was at this level, I had to write it down on the side. And I had to say, okay, 2 over 1, and that's 6 over 3 minus 1/3, and then I did 5/3, okay? I had to write that down. That's okay. All right? It's true. It's true. But I'll be honest, when I actually did that, what I thought to myself was, man, I should know how to do that. And eventually I got to a point where I could without having to write it down. But you have to keep practicing. You have to get, enough exposure to it to be able to do it mentally. All right? And be comfortable and confident that you got the right answer. So this is going to become, and I have not taken a derivative, right? This is just 5x to the 5/3. And now I move on to the next one. I have to do 1/2 minus 1/3.
That would be 1 over 6.
So 1/2 minus 1/3. Get a common denominator. What, 6?
3 over 6.
So 3 over 6 minus 2 over 6, and that's going to be 1/6. So 1/6 for the next. Say again?
Yeah.
1/6. So this is x to the 1/6. The next one, how about we just push the x to the 1/3 up? Make it x to the negative 1/3. It'll just join up with the 7 that's there.
That's legal, right?
Oh yeah.
I just had to put it, okay.
Yep, that's just rewriting it. And then the last one, x to the first power over x to the 1/3 power. Subtract 1 minus 1/3 is 2/3. So minus x to the 2/3. My grandfather was an inventor. He just did his own things all the time. I remember when I was about 11 or 12 years old, he had me go into his shop out in California is where they lived. He had me go out into his shop. He was building an engine with variable valve timing, which at the time had not come out. If you know what variable valve timing is. If you don't, who cares? So he has me standing there with a little camcorder, right? He's like, I need you to record this for me. All right, so I'm sitting there like recording, This is like old school camcorder, right? And I'm just sitting there, I'm like holding it, and he's got an engine with no exhaust. It's just like flames and shit coming out of this thing. And this little, this shop's like no bigger than this room, and it's loud, and I'm sitting there, and so he's running all this stuff, and it all works, and then he turns it off, and he gets a piece of paper, he starts writing things down. He turns to me, he's like, okay, what's 3/8 minus 1? Yeah, and he starts asking me to do like fraction arithmetic, like this stuff in my head, and I'm like 11 years old, and I'm just like, I just remember feeling very inadequate. Because my grandfather expected me at 11 to be able to do that sort of arithmetic, which meant that when he was 11, he could do that arithmetic, Like his expectation of me was so much higher than my education was. And that was just a sign at that time that, man, we have fallen so far behind. You know what I'm saying? Now we're even further. Okay, we're even further behind. Because I'm here in a Cal 1 class, and I know people are going to have trouble with the fractions. I know it, right? It speaks to the times. Hey.
Well, like in high school, up to Algebra 3, they just had us using calculators.
That's right. You're right. I know. And it's a dangerous thing. Yeah, it's very dangerous. Okay, I just erased everything I needed. Okay, it's okay. So let's do it. All right, so we were going to take the derivative of 5/3.
7 plus x negative 1/3. And minus x 2/3.
Derivative time.
Let's see if I remember correctly.
Okay. You want to try that? See if you can get just see if you can get that first derivative on your own. Just you don't have to clean up each one. Just go through and see if you can get them.
Remember, it's n minus 1. It's like n x and n minus 1. So once you get 5x. So it's 5/3 of x. 5/3
Hey, you're talking to yourself.
Yeah, it helps me.
I know, but it distracts a lot of people too. I'm just making you aware of it. I don't know if you know that.
Oh, sorry.
Okay. Well, if you have to take a test, you can't talk to yourself, right?
Yeah, that's basically how I got screwed over, but you're not
Yeah.
getting screwed. I easily started.
Yeah. Yeah.
Remember, I was near a borderline, but I got back on top.
Yeah, I know. I'm just making you aware, that's all. I just don't want you to, some people don't realize that what they're doing. Someone can check my work.
Oh shit, you did them all. Okay, like it's nothing.
Again, I don't expect that you could do that just like I did right there, but you should be able to get to those results. And I'm going to double check it because I did that quick. It looks good. I think on the line below it, I'll write it in a little more detail. That's what you should have been doing. Dropping the power out each time and then subtracting 1 from the power. When you multiply 5 times 5/3, that's 25/3 because the 5 is like a 5/1. 5/3 take away 1 is the same as 5/3 minus 3/3. So I'll come back in and I'll replace all these with what they are. 3/3. This one is 6/6. This one is 3/3. And this one is 3/3. Understand what I'm doing there? And that should give you this up here. We good? I am almost certain that I give a problem like that on the test, because that tests a lot of different things there. That first of all, you're not going to pull the trigger and try and do like some weird quotient thing that you're not allowed to. You're going to split everything into separate terms. You know how to get these exponents correct by using the property from college algebra, and then you apply the power rule properly. All right, we good? You're going to have to practice, right? All right, what's the next rule? That's it.
That's enough though? You don't want it simplified?
I mean, you know, what I said earlier, you know, you could drop all those negative ones down, and you could do that. I'm okay with that as an answer on the test if that's the only thing I want. Find the derivative. But be comfortable. I can't stress that enough. You need to be comfortable simplifying these. All right, the next few are just things that we're going to give to you without any proof as to why yet. I'll prove most of these later. I'm going to prove this one today, why the derivative of sine of x is cosine x. And the rest of these you'll just need to know. All of these are on your formula sheets that you're allowed to have on your test. Reference page 5. If you look at these, all formulas are there, including the derivatives of the trig functions. It's all here. Okay, so you don't have to memorize these, but I will stress to you that if you walk out of this class, you better know these 3 derivatives by heart. Or by mind, however you want to say it, okay? You need to know those. Everyone here needs to know that the derivative of sine is cosine. And everyone needs to know that the derivative of cosine is negative sine, right? Not just sine, negative sine. And everyone needs to know the derivative of tangent is secant squared x. Now the next 3, it would be nice if you knew them, you know, if you had them memorized, but not necessarily essential. These are them. All right? They're on your formula sheet. This sine x cosine x I'll prove. Are you ready to prove the power rule? Are you ready for me to prove the power rule? I know you are. Let's do it. Okay, did we talk about Pascal's triangle? Yes. Okay, so everyone remembers that? Okay. It's in your notes. I'm going to refer back to that. All right? As a reminder, let me see. Did we do the Pascal's triangle for x plus y or x plus h? Can someone look?
X plus h.
It was x plus h? We had found in Pascal's triangle that, if you look at it, we had found that x plus h to the n was x to the n plus nx to the n minus 1 times h plus, we gave up, did we write more down? I don't know if we did. X to the n minus 2h squared plus dot, 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 and at the very end, h to the n. Who has it? Who has their notes? Someone in here takes decent notes. I just want to see what I wrote. Oh, we only went to 5. Did we go to n?
You went farther. I think I'm not wrote down.
Oh, hold on. Maybe I didn't go down. I didn't go down to n. Okay. I didn't go down that far on the triangle.
You went to the 6.
I went to the 6th. Okay.
I got halfway through the 6 and then I gave up.
All right, so look, if you go back and look at Pascal's triangle, the pattern was 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. These were the coefficients. And do you remember that what it was that the powers on the x will come down while the powers on the h come up? Yes or no? Yes? Okay, so if I'm down, if this was x plus h to the 0, this was x plus h to the 1, this is x plus h squared, x plus h cubed, right? Notice a pattern here. Whatever the power was is also equal to the coefficient of the second number. That's an important thing to notice in this pattern. Oops, I forgot to circle this one. The first number was always a 1. And that was always going to be x to the n power out there. And then the next one was always, whatever this power was would be the coefficient. So for here, this would be, let me just show you here. This one would have been x squared plus 2xh plus h squared. That's what that one would have been. So that 2 comes from this. And then the 3 would have been here, right? From that 3. So if we go x plus h to the nth power, the number in front is n. Is that okay? You okay with that? Then the power on x comes down, and the power on h comes up. And that happens all the way across. You buy that? I need you to buy that in order for me to prove this. Do you buy it?
Yeah.
Good enough? Okay, so let's go and try and prove the power rule. It's actually pretty simple once you agree with that. So if I'm trying to take the derivative of x to the n, this means I'm going to take the limit as h goes to 0 of that function, right? But with x plus h plugged in, right? F of x plus h. Do I have to write the definition of the derivative down again? No. So I'm going to plug x plus h in there. Then I'm going to subtract the function itself, f of x, which is x to the n. All of this over h. And I'm supposed to let h go to 0. The problem is that we have to expand this, n factors of it. And that's difficult. But we just agreed that that would turn out to be what? X to the n would be the first one. And then plus, what was the number going to, or what was the thing in front going to be? Whatever power, which the power here is what? N, x to the, now what happens to the power on x? Decreases by 1. So if it started at n, it'll be n minus 1. And what happens to the power on h? Comes up. So we have h. The next term is going to be some number, and I actually don't care what it is. And then I'm going to have x, and the power again comes down by 1. So it'll be n minus 2, and the power on h comes up, h squared. And that keeps happening, right? I'm going to say plus, and I'm going to go dot, dot, dot. That keeps happening until I get to the very last term, which we know for sure is h to the n. Agreed? That's the expansion of this. It looks like this big, ugly thing. But I still have up there what? Minus x to the n. And that's all over h. And do you see what goes away? X to the n's go away. And does anyone have any comments on what's left here? They all what? They all have an h. They all have an h, right? This has an h, that has an h, this one has h squared, it's even better. They all have an h, even the last one has an h. So let's pull one h out. Because I only need one, right, to cancel? So if I pull one h out, my new numerator will be an h and then what? N, x to the n minus 1, right? That's this, with an h pulled out. Plus something in front of x to the n minus 2 times what? Just an h, right? Plus dot, dot, dot. This last one will be h to the n minus 1, because if that was a 10, now it's a 9. If that was 100, it's now 99. And that's what I factored out all over h, right? These cancel. What can you tell me about every single one of those terms? They all go to 0, right? They all have an h, don't they? Yep. Everything down here has an h. This is the only thing that no longer has an h. So this goes to 0, right? It's all gone. And the only thing left is that very first piece over there, which is nx to the n minus 1. And that is the rule, isn't it? That's the rule. The derivative of x to the n is n times x to the n minus 1. Pretty good, right? But you have to have that, you have to believe in that Pascal triangle binomial expansion. You have to understand that first. Once you understand that, then you can do this. All right, what about derivative of sine is cosine? I think I showed you graphically, didn't I? Yeah. I kind of showed you like, look, if you follow the slope of tangent line, it kind of makes sense. But let's do it the real way. So what is the derivative of sine of x? Well, that's the limit as h goes to 0. And I'm going to plug what into the sine function first? What? X plus h. And then I'm going to subtract from that sine x, and then all over h. That's it. Doesn't that look pretty nice? It doesn't look too intimidating, does it? Okay. But we run into a problem. We can't do like the binomial expansion like we did just a second ago. And please do not tell me that this sin distributes through. Okay, please don't tell me that. Any ideas? How about this? Do you remember in pre-cal a formula that we had for sine when you had like two things inside of it being added together? Well, you have your formula sheets, right? So you should look at them. See if any of these ring a bell. Reference page 2. I'm going to let someone find it. Reference page 2. Addition, subtraction formulas. Yeah. What about it? What can you tell me about sine of x plus y on that formula says that it's what? Cosine y. Cosine x, sine y. Now, I mean, that formula is there. I'm not sure if that's going to help us, but that is one way to make it where we won't have x plus h inside the trig function anymore, right? Notice that each one of these new trig functions has just a single term, x, y, instead of x plus y. So let me try it. Maybe that'll help. We have limit h goes to 0. We have sine x. How can I use that formula? It'll be sine x cosine h plus cosine h cosine x sine h minus the sine x that was up there all over h. Now that is correct. That's the correct application of that formula, but did it actually allow me to do anything? Like, I was hoping I would get something like that to happen, right? Because I don't like that. For some reason, that's what my brain is wanting this to go away, but it doesn't. It doesn't mean it's wrong. So watch this next step, okay? You ready? Here we go. My limit involves the variable h, right? So the x's are not impacted by the limit at all, right? It's just the h's. So if I take sine x cosine h minus sine x plus cosine x sine h, that's just rewriting the numerator, isn't it? All I did was I moved this guy onto the other side of this guy, right? Just switch these two, their places. Yeah? And now I'm going to switch it into two fractions. Just tell me if you agree with me that that's still the same. Yeah? I reordered the numerator and then split it into two fractions, but I didn't do three fractions, I only did two, and you'll see why in a second. What do the first fraction here, what does this have in common up here? Sine x. So I can factor sine x out, can't I? Okay, so I'm going to say limit h goes to 0. I factor sine x out. And what am I left with on top? Cosine h minus 1. I pulled the sine x out, right? So minus 1 over h. And then the other one is plus cosine h sine h, cosine x sine h over h. Anybody see this yet? Do you see it?
Can you factor out an h?
Can't factor an h out because the limit involves h. What do you see? Sine junk over junk. Good, very good. That's right here. Remember, I just said a second ago, what is the limit going to? H, right? H is going to something. X doesn't matter, right? X is not controlled by this limit. The limit affects the variable h, not x. So if I just look at this, sine h over h, that's sine junk over junk. The junk matches. Is the junk, are they both going to 0? Yes, so that in red is going to go to 1. 1 times cosine x? Cosine x. Okay, plus, now what about this one? Remember, the junk, not the junk, the only thing impacted by the h is this right here, right? That goes to 0. Okay, so remember